Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Vendors Day, we're going to talk about how the heck you feed power supply to these hungry silicons. So let's dive deep into it. So what exactly is the problem? Well, it does not matter which era or which vector you are looking into it. Most of the CPU, GPU, self-driving IC, wafer silicon or whatever have you, or SoC, they are made very compact and efficient. That's the whole reason for computer revolution. However, the technology that is used, the principal topology, is complementary metal oxide semiconductor, CMOS. Now, CMOS is good and all, but it is very sensitive to voltage, as in most of the silicon system generally works under 2 volt. Let that be very clear. If you want to, you can design to, but it will not allow you to make it small. We want small, so that allows us to allows us to achieve higher efficiency, but does sacrifice voltage resilience. So our voltage is now almost all the time, unless exception, below 2 volt. And again, 2 is the envelope. Generally, you would be 0.8 volt to 1.5 volt. Now, these voltage are like cell voltages. It does not matter based on the size. Basically, you can have a bigger lithium ion cell, still would be 3.2 volt. You can have a very small one, still would be 3.2 volt. Same thing happens here. Now, that voltage is a problem because again, our AC grid, well, first it has its own problem that it's not globalized. There is no global grid. For example, some places you can get 100 volt, some places 240 volt. And if you're in India, poorly regulated places, yeah, the voltage could go from 100 to 300. So that's the problem. Another is frequency. Even that is not locked. So some places like USA, it's 50 hertz. Oh, sorry. It's 60 hertz. In India, it's 50 hertz. And Japan is one of those weird countries, literally has both frequencies. So that's an issue. Our power grid is not, this is the power design silicon that works on it, because again, it's not fixed. So that creates a bridge, meaning you need to take the main power that is available in your wall grid. It has the kilowatts, it has the power. You just need to convert it into some digestible thing for these silicon puppies. We need a bridge. Basically, take the AC mains power, convert it into something that is useful, because not everything is charged by your battery, and not to mention, battery has the same problem. You still have to step down the voltage. So that's the problem fundamentally. And based on the silicon that we are using, can you design a silicon circuit that is resilient to, let's say, AC mains voltage? Of course you can. That's how MOSFET works. It's just that it won't be like your CPU would be this size. It can't be this small. Physics-based, like voltage insulation is physics-based phenomenon. You can't cheat it. So ATX was the first attempt of humanity to fix this part, because again, computers started as early as 1980s or even 70s if you want to be flexible about it. But people figured out very early on that voltage of different things means a different power supply. So a company that is making this will have different power supply. Like Apple is making it, it will have different. HP is making it, it will have different power supply. IBM will make it different power supply. So that created an issue. So how the heck you get AC to regulated DC? Regulated DC means it does not change. You have load variation, it will not change. You have supply variation, it will still not change. That's why regulated DC matters here. It's not just like, oh, I have a, like, you know, 12, let's just say I want a 12 volt output. I will put a 12 volt transformer and connect it. It will not work. The voltage will fluctuate. If AC supply changes, it will fluctuate. If load changes, it will change. You do not need that. What you need is absolute certainty that if I say 12 volt, I mean 12 goddamn volt. And of course, there will be some tolerance, but it will be 12 volts. It does not matter whether the outside voltage fluctuates or my load changes from 1 amp to 15 amps. It will remain in that zone. So that's what we need. So people realized, and Intel that time was a very prolific name and almost like a monopoly. So they come up with the idea. It was Advanced Technology Extended. They created basically a rule book, so to say, a guidebook. And because there was so much mess, every corporation agreed to it, be it Apple, be it basically Compaq, HP, Fujitsu, almost every Tom, Dick and Harry willingly agreed to it, because again, they all wanted it. Because once you make a standard, power supply vendors, be it Delta Electronics or whatever have you, their job becomes easier. And once you have something standardized, other companies can jump into it and say, hey, we can give you something better for cheaper. You won't have a competition if everything is bespoke. If HP has this some weird power supply requirement versus Apple, Apple also has to create their own custom supply, HP also has to create their custom power supply. That was not economical. So ATX was created and everybody happily agreed to it. It's like, yay, that power supply fan pins, the fan pins you see on the 12 volt fan, that's also an ATX. So 12 volt was a very common low voltage, meaning if you look into a low voltage relay, generally it's 12 volt. Look into vacuum tubes, generally 12 volt system or 15. So 12 volt was a very common system, and electric cars were also using it. And internal combustion car electrical systems, they were also 12 volt. So 12 volt was chosen, we're gonna need 12 volt, and everything could design be around it. 12 volt would be the main. However, this was very early on, like silicon were like huge. Like you could actually use a microscope to see it, not electron microscope, just a microscope to see the circuit. It was huge. So voltage resistance was huge. But as technology progressed in 80s, we started to reach into what we call digital logic. These puppy required 5 volt. This is the era where you got the silicon of Arduino. Arduino silicon is 5 volt tolerant. Why? You can design a silicon that can tank 5 volt without any issue. It's just that it can't be miniaturized too much. But in 1990s, that was the cutting edge. So 5 volt rail was also added into ATX. It's like we're gonna have 12 volt and we're gonna have 5 volt. Now, more things happen, more silicon happens, and people start to shrink the silicon. Now, the dielectric barrier becomes even fragile. So they're like, hey, 5 volt is too much. It is punching a hole into the dielectric barrier, because be mindful, voltage only affects insulator. Insulators are like, yeah, we can't tank this. You have to drop the voltage. 3.3 volt became a thing. ESP32, 3.3 volt. So 3.3 volt became the next stage. However, people were like trying to go even lower, even smaller. Now, the final barrier that people agreed on is 0.8 volt to 1.5 volt. So, cool, awesome. But here's the deal. That created a problem. In year 2000, November, people realized the CPU has crossed the threshold, meaning CPU draws so much power that using a linear regulator to burn the power off is not logical. And having basically power supply directly providing a 1.5 volt high amp rail would require copper too much. Like it will require kilograms of copper. So that was not acceptable. So they had to create a system where the item that is consuming the power will have its own regulator, so to say. So your power supply will provide 12 volt regulator before the basically your CPU will convert it down to what it needs to, and then it works. And be mindful, this time a regulator cannot be linear. Before this, it can be linear power supply because they were not that power hungry. But if you are reaching a point where your CPU is consuming hundreds of watt, or that time it was like 100 watt. Yeah, 100 watt at 1 volt simply means you have to have like, or whatever the amp would be, you have to that many amp at higher voltage, like 12 volt, that many amp, burn off 11 volt, that many amp. And I'm like, wait a minute, that's a heater. Yeah, that's why you can't use a linear power supply for newer chips. So there was a hard decision to be made, and the decision was you will have VRMs, voltage regulator modules. And yeah, people hated it because A, it's very complex, and B, it's a switching regulator. Linear regulator burns electricity, while a switching regulator is almost taking AC, taking DC, making it into AC, stepping it down via inductors and stuff, and then making it to DC again. So it's a converter that makes it into AC frequency, basically switch DC, and then does the frequency conversion, voltage conversion, and voila. And that has the benefit, it gives you transformer ability, as in you have high voltage, low amps going in, and you get low voltage, high amps, almost like a transformer. So that made sense. And again, 1995, Intel Pentium Pro started to do that, but that was for server. And for desktop, this started to happen, Intel Pentium 4, I think. And they're like, yeah, we're gonna have 12 volt going into the motherboard, and motherboard will be responsible for converting that 12 volt to 1.5 volt. So this puppy, the VRM became a thing in desktop motherboard in 2000. So why go through all that hassle? Physics. For example, if you have to send 100 watts of power, which again, CPU at that time can hit that, 12 volt versus 1.5 volt translates into 64x lower energy generation, heat generation, so to say, because again, I squared R, I get squared. So you want I to be very small, and that's why we do high voltage transmission. So this 12 volt port that is directly feeding CPU, it's just like a substation basically. This is a substation, or pole mounted transformer that is converting your 11 kV into your 220 volt useful household is the same thing. It's taking 12 volt from the power supply, switching it down to 1.1 volt or 1.2 volt and feeding it to CPU. And this is the easiest way to reduce copper consumption. So wire copper remains small, copper here, it's very small distance. Again, you have to have bonker copper here. Most of the motherboard copper is there, power supply, but it's like centimeters, like barely 3 or 5 centimeter of travel. So you can have good enough shrinkage, and not to mention, because it's spread out, it allows the heat to be dissipated quickly also. So copper content became low because, again, otherwise nobody would be able to afford it, and this allows. And as switching regulators became cheaper, as in MOSFET became cheaper, diodes became cheaper, and the IC, the dedicated regulator IC becomes cheaper, this became a no-brainer. Everybody just agreed to it. This was the paradigm shift, where it's like, okay, power supply will no longer provide you the bulk of power in the right voltage. It will give you a high voltage rail, and you're gonna step it down. That's what happens with all the silicon in your GPU, NPU, CPU, whatever have you. And it will happen on the same AI data center or whatever have you. So this is the legacy of ATX that we use right now. So how do we actually achieve it? Because again, you have to understand that as power demand grew, linear power supply gave up. It's like, yeah, I can't do this. So we replaced it with switching power supply. Switching power supply does have the problem. It switches, it's going tick-tock, 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 tick-tock. So that creates a ripple. Ripple, silicon, no bueno, kaboom. So what do we do? And here's the problem. You have to drop from 12 volt to 1.2 volt, meaning off time, especially if you are using PWM system, there is a lot of dead time. Where it's like you're 12 volt and you turn it off for 90% of the time. And like, how the heck power goes from, yeah, it's draining from a capacitor and inductor. And problem with that is your voltage is dropping. So, and you charge it on, dropping, charge it on, dropping. And you're like, wait a minute, that's a very ripply thing. Yeah, idiotically rippless. So, two things were chosen. First, because again, the current requirement was so high, and again, I squared R, people are like, hey, what if we split this puppy into like multiple phases, like 3 phases, 6 phases. Some stupid motherboards have like freaking 24 phases, my man. So you will have multiple phases. Benefit of that would be current would be spread out. And again, current has disproportionate relation to heat generation. It allows you to use smaller component and less waste heat generation. So that's the winning composition. That's why you have multiple phases. That's one thing. Better load sharing, basically, is cheaper, because again, finding an inductor that is rated for 100 amp versus finding an inductor that is rated for 10 amps, 10 amp would be exponentially cheaper and smaller. So that's why we started with phase. Second, why we have 3 phase, it's basically we interleave it, meaning instead of having each phase going on and off, we offset them. Like exactly how your 3 phase AC mains works, where it's like each phase is 60-degree offset. Benefit, you never go to 0 volt. Benefit, the ripple gets cancelled out. Meaning if one phase is starting to low down in voltage, as in its capacitor is reaching lower stage, second phase would be like, I got you fam. It goes into on phase. It's like, I got you. It turns it on. And then when it starts to go offline, it's like third stage is like, I got you. So it's a relay stage. It's like tuk, 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 tuk. And voila, the minimum and maximum voltage tolerance is very tight. And benefit of this is tight from both sides. As in your 12 volt rail can dip a little bit, this puppy will tank it. The CPU can go from, oh, I'm barely drawing 1 amp to 100 amps. This will be like, I got you. No ripple, it will tank it. So this is the easiest way to beat the noise performance of a linear regulator while not having bonkers amount of ripple. And again, this is the only way to do massive conversion, like 12 to 1.2 volt. And that's why if you look into motherboards where they have like voltage control for overclocking, the numbers are so huge, like 1.2639. I'm like, why the heck you have so many steps? Because you have so many phases. It makes it easier. So each stage is interleaved, so there is no overlapping, meaning 2 stages will never turn on at the same time. They will turn on at a different time, and it reduces the ripple. That's the whole thing. Each stage is very ripply, but combined all of them, ripple goes down, and you have bonkers robustness under high load condition. So CPU could be like, I'm energy saving, then you load crisis. It's like, I got you fam. The VRMs are like, I got you. You want physical demonstration? Please look at the video links down below. Now we have the modern tragedy, which is 12 volt high power rail. This puppy was a penalty of GPU becoming stupid. Like how we got VRAMs because of the CPU becoming stupid in terms of power hungry, GPU became stupid, and they're like, yeah, we need something better, because these connectors were becoming first huge, and now we had some graphics card that had 3 of those puppies. Like, yeah, we need to handle this. So 12-volt high power rail connector was created, and it was specifically designed to feed 600 watt of power without too much hassle. Now, again, who came up with this? Intel did not, Nvidia did. Now, Intel, because again, it's huge and people want to like with it, there is another branch also, which is PCI SIG, basically Personal Computer Interconnect Express. So that PCI interface, that they also have an association, like how you have Bluetooth association, USB association, they have the association. Nvidia went to them, it's like, bro, you have a problem, me have a problem, let's solve the problem. Let's create a new standard. And Intel agreed. So new standard was created, ATX 3.0. This connector was added. Now, for some reason, Nvidia was smoking something bad, like not good weed, some bad. And they did dumb stuff. Like genuinely, how the heck that happened? Now, best explanation people have is like the engineers that were good, they were shifted into AI system, or they retired. Again, compare what Nvidia did with this 12-volt system versus their own older system. You'll be like, who is the supplier? Like, we have to ban that supplier. That's bad joint. So here's the, under no circumstances, a faulty plug should cause any issue. It's like, wait, why? Everybody's like plug fault. No. Again, we had multiple pins, 12-volt rails, 3 of them, and never ever this happened. Why? Because power supply was designed properly. And I do not mean power supply of the computer, I mean power supply of the GPU block. As in, normal GPU, when it's built with a brain, logically, as in AMD, Intel, older Nvidia, they had a very simple idea. They had multiple phase, exactly like CPU, and they distributed the phase across the pins. The idea is this puppy will have, let's say, 2 phase. This puppy will have 2 phase. That puppy will have 2 phase. 6 total phase. Each phase is divided into these power rail. Now, assume worst case scenario. Let's say you plugged it in, connector was not connected properly, only 1 pin was giving power. VRM turns on, it waits for signal from all the data. It's like, whoa. 2 of my phase is not behaving properly. Shut down the GPU before it boots up. It's like this will happen on millisecond, not millisecond is too slow, microsecond. It's like, bro, I tried to turn it on, nothing happened, because again, I'm supposed to get voltage from all my phases, I'm not getting it, shut down the GPU. The end. No fire hazard, no melting hazard, nothing. So what Nvidia did is, they took the 12 pin that should have at least ideally separated in 12 pins, if not at least basically 3 pair of 2 pins should have been separated. And in that scenario, if 1 pin was connected, others were disconnected, the VRAM stage would be like, I'm not receiving voltage, I'm turning off. That did not happen. This was a gargantuan design fail. And if you have seen Linus Tech Tips, it's like, okay, I'm going to replace this 12 pin with a DC connector. And it's like, hey, wait a minute, why the heck PCB has only 1 point? Yeah, you could not do that with old GPUs. You could not, you can open it up. I have linked the video down below of a person actually showing the motherboard, I'm saying PCB and all that. Again, this will be connected to something else. This would be connected to something else. That would be connected to something else. That's logical. That's how it should be. So in case there is a imbalance, VRM detects it and it's like, yo, something is off. Let's turn it off. And then that's why generally PC repair guides were like, hey, have you tried pulling out the power plugs and plugging it back in? Because again, if there was a poor seat issue, that would be fixed it. So fundamentally, again, Nvidia, the worst part is that Nvidia realized that this is a problem. World realized that you cannot just melt $1,000 cards like this. So Nvidia is like, okay, what if I piss on you? What if I added 4 pins extra, sense pin? Now be mindful, these pins are 100% useless. That's why they were not there in ATX 3.0. It's like ATX 3.1 now. So this pin screams, do not draw more than 400 watt. Do not draw more than 600 watts. What's the point? Like we had a older standard, older logic, and you had to change nothing. Like this was from Nvidia, you shall follow the reference design where we F the customer. This was like, again, either the person who was designing older Nvidia power rails retired or they were shifted to AI system. There is no reason why this sort of stupidity ever happened. Like this was, are you serious? Like, are you genuinely serious? And be mindful, by the way, older Nvidia, they were so anal about power balancing. They had MOSFETs switching these systems, meaning if for some reason you are getting like 80% and over, like they will have current sense and they're like balance the load. To modern system, short everything to 1 point. Again, there is nothing wrong with shorting everything to 1 point, but have thick connectors. Why have 6 pin? Why? Like thou shall not have 6 pin. If you are like, hey, I only want 2 points, great, but have 2 thick puppies, like AC mains equipment, like 2 thick points. This was just a design failure. This is like bad. This is like Nvidia. First, Nvidia messed up. No problem. Things happen. They did not fix it. They doubled down. You add extra money on this. That was genuinely why. Like, I'm starting to reach that point. Like, people say, no, there are no adults in this room. It's like, and again, I'm listening to Jensen Won because again, he would have seen it, like how badly this was being received. And again, reputation matters for stocks. It's like, nah, poor people die. It's like, it was sad. Like, we had better solution and you effed it up. And all it would have required is like nothing. Basically nothing, like flat out. You did not have to dig your grave, but they did. So what can we expect in the future? Well, again, same thing is happening. AI is becoming stupid. So we had like 600 watt. Now they're like, hey, what if we have 100 kilowatt in one power supply rack? One rack server unit. So that went stupid. Now 12 volt is no longer enough. So they're like, okay, now let's switch to 48 volt main rail system. Now here's the deal. Why always 48 volt? You must have seen like people are trying to, like, if Mercedes has this, where it's like, okay, 12 volt system, throw away, put 48 volt. Tesla also does that 48 volt system on Cybertruck, and newer trucks, they will also do that. And more people are doing 48 volt. Look into USB power supply, power per delivery, so to say, PD. 3.1 standard has 48 volt. But why exactly 48 volt? Yeah, that's below what we call safety external low voltage. So safety extra low voltage, meaning if you have a cable, the conductor does not give a damn about the voltage. Okay, conductor only gives a damn about current, amps. But insulator, this puppy gives a damn about voltage. So if you are below 48 volt and you touch the terminals, you go like, touch terminals like this, nothing bad will happen to you. You can touch your car's battery terminal, nothing bad will happen to you. Simply because 12 volt cannot jump your skin. Up to 60 volt, nothing can jump your skin in ideal scenario. Don't experiment with babies. But then why 48 volt? This is for lead acid battery system, because at 48 volt lead acid, meaning 4 lead acid batteries connected in series, the charging voltage will touch, give or take, 58 volts. At that point in time, even if you touch it, you should not get electrocuted. But that's the upper limit where it's like, whoa, whoa. And be mindful, if you're designing a power supply, you have to assume for some worst case scenario. You have to have some buffer, because spike happens, ringing happens, MOSFET rings for some reason. So those sort of things can push the voltage higher. You do not want to, like, oh, I touched it and like, bam, me died. So 48 volt is the highest voltage you can go safely without going into live territory, as in insulation cost becomes exponentially higher and safety regulation becomes brutal. And in case of server, nobody can touch the server if server is on, because server is mostly made out of metal. So you have to have like high insulation gloves for changing hard drive. That's not acceptable. So 48 volt is the upper limit. We cannot exceed that. These for me cannot exceed that. So server companies are like, okay, now we are going to 48 volt. They can't go higher because again, they do want the ability to person touch that. And again, going from 12 to 48 volt gives you 8x reduction in current. Everybody wins. Now, then why don't we do that with our desktop? Because given the fact that laptops are switching to that in 2028, why don't we do that? Frequency. 12 to 1.2 volt, the jump is bad. But again, silicon frequency can do that. This 48 to 1.2 volt, that jump is very high frequency, meaning if you have low enough frequency, ripple would be bad. Does not matter how many phase you have. Like again, you can solve it by having 100 phase, but that's not logical. So what is logical? Same amount of phase count, but frequency has to go up. How high up? Silicon MOSFETs will not do. You have to use silicon carbide or gallium. And not to mention at very high frequency, ringing becomes an issue, induction becomes an issue. You can't even use 3-pin MOSFET, you have to use Kelvin connection MOSFETs so you can switch it reliably. So all of those becomes a hassle. AI puppy can endure that expenditure. We can't afford it. So that's why your computer is not going to get that. In your laptop, it still only does one conversion, where 48 volt to whatever lithium battery voltage would be, which generally is 19 volt or something like that. So that's why 48 volt for household, that's not happening anytime soon. Again, I do expect that to happen eventually, but not anytime soon. But what about major manufacturers on the desktop environment? Dell, HP, Lenovo, they are going to server, exactly like how Pentium did in the long ago. It's like throw away all other useless voltage. You have 3.3 volt, 5 volt, negative 3.3 volt, negative 5 volt, standby voltage load, throw all of those away. It's like, well, why? Well, the idea is PSU, as in the power supply unit, can be very efficient if it's only designed for 1 voltage. Meaning, right now power supplies are rated for 80%. That's why that 80% platinum, that's the whole point. At 80% load, it should be this much efficient. Okay, cool. But what if you want more? What if you want at low loads? If you have multiple voltage rail, like you have 3.3 volt, 5 volt and 12 volt, it's very brutal to design a power supply that can be efficient. Physics will not allow you to, like, no. But if you have single power rail, 12 volt the end, you can allow the power loading to go down very low and still be efficient. So company like Dell, HP, Lenovo, they sell thousands of them. So if they say we are saving 1 watt per hour, that's short of take money. That's a lot of money. So they have all switched to 12 volt system. Now Intel realized that 12 volt system eventually will make it into desktop also. So new standard has been created, which is basically 12 volt VO standard. Basically this ATX has this standard. It is parallel to normal ATX, but it will become dominant eventually. Not today, eventually. It will happen because servers were already doing it. That's why servers have hot swappable system. They're like, okay, but they have like 2 spade connectors, like big puppies. Those are 12 volts, but they have a lot of tiny pins. What are those? Well, there's a sense, handshake, and those are in those natures. It's not what you call 5 volt or things. It could have that, but again, those will be just for sensing, just for handshake. It's like, you know, how your USB-C connector has a CC pin for handshaking. So it does not directly give 48 volt to your mobile phone and booms it. So that's why these things are hot swappable. They have only one primary voltage rail. And look into the back of it is like these spade connectors. Yeah. Look into those 48 volt big spade connectors. And again, they do have some sense wiring, but generally 48 volt. So servers are already doing it and it's logical. Dash like, you know, high power efficiency. And 48 volt is a bit too far away. It could come down in price, but I would still not hold my breath. I can hold my breath for this ATX 12 volt. The idea is if you need 3.3 volt, make that 3.3 volt there. And if it's a very low power, like let's just say you need 3.3 volt for something, some IC or something, but it's very low, like let's say 1 milliamp of power draw, use LDO, low dropout regulator or linear regulator. You don't need, like, you know, expensive switching and all that. If low current, high current, no. High current, you have to go to VRM. But low current, you can do that. And that's desirable. So your main power supply becomes efficient. So that's the future. So this was my presentation on basically how the heck we feed power to these hungry puppies. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you have enjoyed it, click the hype button. If you didn't enjoy it, I would urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.